All right, today we are cracking the code on a really fascinating class of molecules, coordination compounds. I want you to imagine a tiny molecular safe that holds its contents under lock and key. And guess what? We're about to figure out the combination.
So let's start with a little puzzle. If you dissolve a simple salt, something like potash alum, in water, it just completely falls apart. All its ions just scatter and swim around. No big deal. But coordination compounds, they are a whole different beast. When you put one in water, a core part of it stays locked up tight. It's like a chemical safe that just refuses to open.
So that begs the question, right? What is in this chemical safe box, this coordination sphere, as chemists call it? And what on earth gives it this incredible stability? Let's take a peek inside.
To answer that, we need to meet the key players that make up this incredibly stable little structure. It's time to break down its anatomy. Right at the heart of our safe, you've got the central metal ion. You can think of it as the treasure that's being protected. In the example we're using, it's an iron ion, and it acts as the anchor for everything else.
Now, guarding that treasure are the ligands. These are molecules or ions, in this case cyanide, that form these incredibly strong bonds with that central metal. They're like a team of tiny, super dedicated bodyguards. And the total number of these connections, the bonds that these ligands form, that has a special name. It's called the coordination number. So here, with 6 cyanide ligands attached to the iron, the coordination number is, you guessed it, 6.
So how do these bodyguards stick so tightly to the treasure? I mean, what's going on there? To understand this really powerful bond, chemists actually use 2 different models. Think of them like 2 different sets of blueprints for our chemical safe.
Okay, first up, we have valence bond theory, or VBT for short. This whole model is about orbitals, those paths that electrons take, mixing and merging together. It's like the metal's own orbitals blend, or hybridize, to create brand new shapes that are just perfect for bonding with the ligands. And then you've got crystal field theory, or CFT. This one focuses more on the electrical forces at play. It looks at how the negatively charged ligands kind of push and pull on the electrons in the metal's orbitals, which changes their energy.
Now, the really cool thing about VBT is just how much it can predict. By figuring out which orbitals are going to blend together, chemists can predict the final 3D shape of the entire complex. This theory is exactly why we know these compounds can form such specific, really fascinating shapes, like a tetrahedron, or even a more complex octahedron.
But VBT kind of hits a wall. For all its power in predicting shape, it can't quite explain one of the most striking things about these compounds. They're often super vibrant and beautiful colors. For that, we need to switch blueprints and turn to crystal field theory.
And this, my friends, is where we unlock the secret to their color. It's a fantastic story of energy, light, and electrons taking a little leap of faith.
Okay, picture this. Imagine the metal's 5 d orbitals. These are just specific pathways for its electrons, as 5 race cars, all idling at the same energy level. But as the negatively charged ligands get closer, their electric field basically splits the racetrack. Some of the cars get pushed onto a lower, more stable track, while the others are forced up onto a higher, more energetic one. And this creates a very specific energy gap between them.
And the crucial point is this. That small, precise energy gap that gets created, that is the entire secret. It is the fundamental reason these compounds have color. It is all about that gap.
So how does an energy gap create color? Well, when white light, which has all the colors of the rainbow, shines on the compound, an electron on that lower energy track can absorb just the right color of light, the perfect little packet of energy to jump across the gap to the higher track. The colors that aren't absorbed get reflected back to our eyes, and that creates the vibrant hue we see.
Think of it this way. If a compound absorbs yellow light to fuel that electron jump, the light it reflects back to us is whatever is left over. And what's left over from white light when you take out yellow? It's complementary color, violet. It's like the compound is eating one color from the rainbow and showing us the rest.
Okay, so these theories do a brilliant job of explaining the stability and the color of these chemical safes. But why does any of this really matter? What's the big picture here?
Well, these 2 models are just incredibly powerful. They let chemists predict a compound's shape, its magnetic properties, and, of course, its color. And this isn't just some abstract chemistry lesson. This stuff is fundamental to life and technology. The hemoglobin that carries oxygen in your blood, that's a coordination compound. So is the chlorophyll that powers photosynthesis. And in medicine, compounds like cisplatin are critical coordination complexes used to fight cancer.
It's really incredible when you think about it. A simple question about a box that won't open in water leads us to this profound understanding of color, medicine, and even life itself. It's a great reminder that even in the most familiar things, there are these hidden worlds of complexity and beauty just waiting for us to discover them.